Hello, my name is Ethan Chinnis, and this is Lab 3 Circuits. The purpose of this lab was to demonstrate that the current and voltage in various circuits containing capacitors and resistors, and we used multimeters to measure the current and potential difference. The results were that the current was the same across the whole system, which makes sense. The sum of potential differences were very close to zero, as they should, and the charge and discharge times for capacitors were the same, as they should, with obviously proportion to how much the resistance was. The principles for this lab was the node rule, where that the current into a point is equal to the current out of it, so the current is conserved. So the loop rule, that the voltage changes around a current can all be summed equal to zero. Ohm's law, which is V is equal to IR, which is V is volts, I is current, R is resistance, and capacitance Q charge is equal to the capacitance times the volts. The first circuit was the series circuit, which you can see here with the two batteries, 2 ammeters, and a 47 and a 100 ohm resistor. The system was the battery, wires, ammeters, and resistors, and the surroundings is everything else. So the predicted current should be that the two batteries, 1.5 volts each, divided by the total resistance is equal to 2.04 milliamp current. The actual data was that the batteries were 3 volts. The resistance potential difference for the 47 ohm resistor was 0.927 volts, and the 100 ohm 1.95 volts, which added together are very close to 3. So 3 minus 3 is equal to 0. So that checks out. And the currents were 19 milliamps for the first section and 19.2 for the second section, which are really close, which makes sense because current should be the same around the whole circuit. And backwards, it equals negative 19, which makes sense as well, because when you reverse it, it just becomes negative. And here's the potential difference graph. So once you get to the 47 ohm resistor, it should drop about 1 volt from 3 because it was 0.927. And then it's constant until it gets to 100 ohm, which then it drops all the way rest to 0. This is what it should look like. And then it should be 0 the rest of the way. The ammeter doesn't change when adding a voltmeter because the current is constant in a closed circuit, which when we did this, it equaled 19.3, which is very close to 19, which was about the other two were. And in parallel, it now equals 50 milliamps because we have a new equation which is 1 over the resistance. And when you calculate the resistance of each element, 0.927 divided by 0.09 is equal to 48.7, which is about 47. And for the 100 ohm, 102.6 is what we measured, divided by, with 100 ohm is equal to 102.6 when you do this equation with its stuff, and that's almost 100, so that makes sense. The other circuit was this RC circuit, which if I play the video here, the bulb starts to glow a little bit and dims. And that is because as we charge the capacitor, the light bulb starts bright because there's a massive current coming through. Not a massive current, but there's a decent amount of current coming through here. And then it dims because the capacitor is charged and now it no longer takes a current. And as it discharges, the light bulb lights back up as it's discharged because it's now letting current out back into the light bulb. And the charge time of the 10 ohm resistor, or it's supposed to be 10 ohm, but our light bulbs are actually 1.8 and 5.4 ohms, which for the 1.8 ohms was 0.5 seconds, and the bulb 2, 5.4 ohms, 1.5 seconds. This makes sense, 3 times the resistance, 3 times the charge time. And the discharge times also check out here, 3 seconds to 9 seconds. The possible error in this lab, human error, could come from not attaching the clamps from the wires 100% perfectly because they have these little metal clamps that have to attach perfectly to these resistors. And then also, it shouldn't happen, but there could be equipment error. We don't know for sure, but it could happen where the multimeters don't necessarily measure 100% accurately or conserve charge. And also, you'll see here in a minute that they actually do have some resistance when we count them as having 0 resistance. And if you charge a capacitor with no resistor in a circuit, it theoretically should charge instantly. That's the what if question. It should charge instantly. However, in real life, this isn't happening because of the slight resistance in the ammeters and the limitations of real-life capacitor. And that's also where the error comes from a little bit here because it does have a little bit of resistance, which is why some of our numbers aren't exactly the same when they should be. Whereas you can see back here, these should equal 3, but because of the little bit of resistance from these things, it doesn't quite equal 3. And that is all.